Good morning. Dr. Stewart back with you today. And today we're going to study and do some problems having to do with motion, but a very specific type of motion. That is the type of experiment or activity that involves a moving object against a force of gravity that is actually put into motion by either a mechanism, by a human being, whatever. It's called the projectiles. It's a classic problem that's done in physics right after you learn the kinematic equations. Now, we're in the fall season of 2020, and because of pandemic, sports have been shuffled around schedule-wise, and as we are in the fall, which typically would be the beginning of football and the end of baseball, we have all three sports plus hockey all coming together during this time frame. So I brought some props to sort of remind us of the motion of things, and we're going to use sports as an example. Football, we usually focus on the quarterback who can hit a moving target, very fast wide receivers, and by taking that ball and using proper technique and throwing it, it can arrive at the same spot that someone running at full speed can pull that ball in and go on for a touchdown. This is an unusual shape. It's an ellipsoid, and the reason for that is to minimize air resistance, and the spiral gives it control as it goes through the air. A second sporting object is a golf ball. We just had the U.S. Open Championship won by DeChambeau, who is a physics major and models his golf game after the laws of physics. And this golf ball is hit by a golf club, and it goes through an arc and then comes down, hits the ground. Pro golfers now can hit these balls regularly well over 350 yards. So that's 3.5 football fields. We are just starting the playoffs in Major League Baseball, and so not only do pitchers have to understand the physics of projectiles and the effect of spin on the movement of the ball, but the batters have to know at what angle they want to launch the ball with the bat to get maximum flight to go over the fence in a ballpark. So these are just the types of things that we do in sport. Now, basketball will start soon, and obviously with basketball, having the touch of shooting, especially like a foul shot, 15 feet away from the basket, putting the proper arc and proper spin on the ball to make that go into the basket. Sporting events are great examples of physics, and we're going to use that to illustrate the world of projectiles. Okay, so we're going to start with a reminder of the kinematic equations, which I've put up here. We derived these in a previous class, and we're dealing with quantities, which we put into variables. We have velocity, v1 and v0, v0 being the initial velocity and v1 being the velocity after some acceleration has taken place. A stands for acceleration, and we'll be doing things in the metric system. So in gravity, that is going to be 9.8 meters per second. T is for time in seconds, typically. If you want the average speed or average velocity, we can take the two velocities, the initial and the final, and add them together and divide it by 2. A very useful equation is the distance that something travels is equal to the initial velocity times the time that it is in transit, plus 1/2 a acceleration t squared to give us that calculation. The thing to notice would be the units of these quantities. Obviously, distance would be in meters. Velocity is in meters per second, so when you take meters per second times second, the seconds cancel, and so we get meters. So this unit corresponds with that unit. And when we go to the second term, we have 1/2, that's dimensionless. Acceleration is meters per second squared, so there's s squared on the bottom, and then on the top is t squared, so the second squared cancels the seconds squared, and that gives us, again, meters for a consistent unit representation of that equation. And finally, we have the final velocity squared equals the initial velocity squared plus twice the product of A, acceleration, times the distance traveled. So we'll refer to these when we get into the issue of the projectile motion. Now, we have to understand that when we're dealing with projectiles, we're definitely dealing with vectors, okay? And a vector is a quantity that has both magnitude, how big it is, but it also has direction. So we are going to keep that in mind when we're dealing with these particular variables. They are vector quantities, and when we work with them, we have to take into account not only the magnitude, but also the direction in which it is pointing. Okay? So let's start with a typical problem, and that would be such as a punter that would be punting a ball at the end of a series of downs to give it back to the other side and have it go as far down the football field as possible. Okay? So if we draw a little picture of that, we have a level ground. We're going to just use an arrow to represent the motion of the football as it comes off the punter's foot. And we're going to call that V, just V, for, we'll give it some subscripts here in a second. And one thing that's going to happen with that ball is going to go through a parabolic shape, okay? Meaning this is going to have the shape of a parabola, and it will come up to some total height, meaning highest point, the apex, and then it will come down and hit the ground, and we're going to use the term R to represent the range. So the range would be the distance that it goes out here, and I'll put that R there. Okay? So, when we're launching something, we are launching it, and it has one velocity as it leaves the foot or leaves the hand, but we are going to break that one velocity into two pieces. And we're going to do that using the proper techniques of vectors. Okay? So I'm going to draw this V down here. There's my V, okay? And then I'm going to drop a perpendicular down to the ground. And I'm going to form a right triangle with that, okay? So this is going to be my hypotenuse of that right triangle, and I'm going to label these two sides. This right here, since it's going in the y direction, we are going to call that V sub y. Now let me put a little coordinate system here. Typically, we do up and down in y, and we do left and right in x. Okay? So that's our typical coordinate system. And the component of this velocity, which is in the direction of the hypotenuse, we are going to label as Vy. And then this component we're going to label as Vx. Okay? Because it's the portion of V that is actually traveling in the x direction. Now, let's do this to extremes a second. Suppose this triangle is straight up. If it were straight up, then we wouldn't have a triangle. We'd have something that's going straight up and straight down, and there would be no Vx. Vx would collapse to 0. If we had something going straight out, then it would have no initial vertical velocity, and all of its velocity would be in the Vx direction. Now, when we have something that's going at an angle to our horizontal, we now will have some angle here, theta, which describes how far up above the horizon we are going from 0 all the way up to 90 degrees. A punt that went up at 90 degrees would not be too effective. It would come right back down to the punter. And a punt that went out at 0 degrees would not be very effective because it would go right into the back of the lineman. So obviously the punter has taken years to develop the proper technique to get the angle of that punt going at just exactly what gives him or her maximum range. And of course you also hear the notion of hang time. So there's always a correlation or a connection between hang time, which gives the football team that's kicking the ball time to get down and cover the punt, okay, and that would like to have the ball as high as possible, but the range, how far can you get it down the field, is also a consideration. So the balance of those two is what the football punter is trying to develop and execute. Okay, so let's come back to the triangle here with some angle theta. Okay, we can find what these two components are using trigonometry. So we're going to take this Vy, which is the opposite side of the angle theta, okay? We're going to divide it by the hypotenuse, V, and we're going to say that is a trig function. Opposite of hypotenuse is sine theta, okay? Well, if we solve that for Vy, then Vy is equal to V sine theta. All right? In a similar way, we can look at the horizontal component and form Vx, the adjacent side, divided by the hypotenuse, V, and that is the cosine function, adjacent over hypotenuse, so that is cosine of theta. And again, we can solve for Vx is going to be equal to V cosine of theta. All right. Now, why did we even do that? Why did we take the time to find the components of the velocity in the two directions? Because in projectile problems, it is convenient for us to take the actual motion and divide it into two pieces. One piece is the piece that is actuated by the vertical component of the initial velocity. That part that is making the projectile go straight up and down. And then there's another part that we're concerned about, and that is the horizontal component of that velocity, and that will give us the component that actually makes it go in the horizontal direction. So we're going to divide the motion into those two pieces, and this is the way it's going to go. Our first step will be take the known velocity, and we will find the two components. That's what we do every time. Take the initial velocity, use trigonometry and your understanding of right triangles to find the two components. Then isolate the vertical problem into a straight up and down problem and find out how long that object is going to be in the air. Okay? We'll see how we do that in just a second. And then once you have that time, then take that time and use the kinematic equation to find out how far it will go due to this horizontal component for the time that it has traveled up and down. Okay? Now, here are the things that we need to appreciate. The vertical motion, with its initial vertical component, it is acted upon by the acceleration of gravity, but in a negative way. So as it starts out, it will have a vertical velocity, and gravity will slow it down until it gets to its height, and it stops instantaneously. So we're going up very fast, slower, slower, slower. We stop, and now we start coming back down, basically replicating the upward motion, but in the opposite direction. So once we get to the top and stop, we'll then start accelerating down, and when that vertical motion would hit the ground, it would be the exact magnitude as the initial vertical velocity up. Now, that's the vertical. We do have acceleration, and we'll have to use the proper kinematic equation for that. The horizontal motion, there is no actuating force on it. It's just going horizontally. There's no big star out there grabbing it and pulling it along or something retarding it. So it is going to go at a constant velocity during this whole motion. So as the ball is going up and down in that parabolic motion, the progress horizontally will be at a constant velocity. That makes that a very easy calculation, just using our typical understanding of distance equals rate times time. So that's how we're going to approach this. So let's take a real life example. Let's say that we have a flat surface. We're going to launch some projectile with some velocity, and we'll say it is 50 meters per second at a 60-degree angle. So it's going to be upwards, okay? And we're going to try to predict where is it going to hit. Where is that going to hit? So we want to determine the range and along the way, we'll do a couple other things. We'll find out how long the projectile is in the air, hang time for the punter, and we'll also find what is the distance, the maximum height, or the apex that the object will take. In golf, for example, when they do the tracing of the ball, the computer will read out the apex, or the maximum height of the golf ball, and also its speed, and then range down the golf course. Okay, so first thing we'll do, step one, so I'll just put a big 1 here. We will take this initial velocity and we'll break it into its two components. Okay, so let's draw a little triangle. So here's our 60 degrees, 60 degrees. We'll put 2 little arrows there representing the components, and we'll put this as the hypotenuse, okay? So going back to our formula here, we can find Vy, which is going to be V, which is 50, times a sine of 60 degrees. So that's times sine of 60 degrees. We'll work that out in a second. And Vx is going to be 50 times cosine of 60 degrees. Okay? Now we use our calculator, and for 60 degrees, if we go for the sine, that's going to be 0.866. So this is going to be 50 times 0.866, rounded off, and we'll take that times 50, and we get 43.3. meters per second. Now notice the hypotenuse velocity was 50. The vertical component, which we found Vy, is 43.3. So it's less than what we started with in this direction. We would always have that. But remember, the hypotenuse is always the longest side in a right triangle. Let's do the same thing for Vx. So that's going to be 50. And we want the cosine of 60 degrees. So 60 degrees, cosine right there. And that's 1/2. So that's times 0.5. So that's going to be 25 meters per second. So we now have the two components. That's step one. Always do that. First step, break your initial velocity into two pieces. Second step, let's analyze the vertical motion. Okay, we'll do that with a little different color here. So here's what we have. We basically have something going straight up with an initial velocity of 43.3. All right? And we're going to ask ourselves, how long does it take until it stops? Where does it stop? It stops when it's vertically, when it's at its maximum height. So let's find out what that time would be. Well, what can we use over here in our kinematic equations? Well, our first equation says that the final velocity is equal to the initial velocity plus at. That might work for us because we can solve that for t. So let's take that. v1 equals v0 plus at. Okay? Let's solve for t. v1 minus v0 divided by taking v0 the other side, making it minus. Now we're going to divide by a, and that will be equal to t. All right? Well, let's see what we have here. The final velocity is going to be 0 because we said it stops at the top. Vertically it stops. Okay? So this is going to be 0 minus its initial velocity straight up, which is that, 43.3. Okay? Divided by the acceleration. Well, the acceleration is not making it go faster going up, but it's slowing it down. Therefore, it's a negative acceleration. It's like putting the brake on in your car. So this is going to be a negative 9.8 meters per second squared. And that's going to equal the time that it takes to go up to its height. So let's see what that would be. That's 43.3 divided by 9.8. And that's 4.42 seconds, rounded off. 4.42 seconds. Now that would tell us that its total time in the air would be the time up plus the time down. Because of the symmetry of the motion, going up is the same as going down, but just reversed. Okay? We can then say that the total time is going to be twice that, or 8.84 seconds. Now what can we do with that? Well, we know what the horizontal velocity is 25 meters per second. And we also know there is no acceleration, either making it go faster or making it slow down. So we can then find the distance that it travels. That distance is just going to be this velocity, 25, times the time of which it traveled. So that's going to be 8.84. So let's see what that is. So 25 times 8.84. 221. So over 2 football fields. That's what we're looking at here for this type of launch. Again, ignoring air resistance. In most projectile problems, especially in introductory physics or in high school physics, you will not get into the heightened complexity of air resistance, which makes it a fluid flow type of problem, and that is only addressed when you get into, say, your sophomore or junior year of college in an engineering course of study. Okay? So 221 meters is the range, how far this would go. I also mentioned we'd like to find the apex or the height. Okay? Well, how can we do that? One way would be using the fourth kinematic equation. We'll do that with step 3 down here. Okay? Let's find the height. Well, let's take this equation and solve for the distance. Okay? So we have v1 squared equals v initial squared plus 2ad. So let's solve for d. Let's bring v0 squared over here. So we have v1 squared minus v0 squared. We're going to divide by 2a. And we're going to say that equals the height at the top of the motion. Okay? Well, what do we know about these two things? The final velocity is 0. So we said it stopped up there. Okay? So we can say that's 0. So this distance then, going up, is going to be equal to minus v0 squared. Well, what is v0? That is the vertical component, which is 43.3. So that's 43.3. We're going to square that. Okay? We're going to divide that, and actually this should be outside here. Just going to square the actual magnitude of the velocity component. We're going to divide that by 2. Now, acceleration is negative, so it'll have a negative sign on the bottom. That'll cancel those 2 out, and that's 9.8. Okay? So let's see what we get for that. We get 43.3. We're going to square that. Is 1874.89. We're going to divide that by 2 times 9.8, which is 19.6. So let's see what we get when we do that. Divided by 19.6. And we get 95.65, and what would that be? Meters. Okay. So how high did it go? A little bit less than a football field in height. Okay. So let's review the steps. Understand the problem, understand what your initial velocity is and the angle at which it is launched. Take that triangle, find the 2 components, the vertical component and the horizontal component, get your numbers for those. Then focus on the vertical motion only. Use our first kinematic equation solving for t, and going through and remember to keep your signs straight. One thing you'll know is time will always come out positive. We won't have negative time in this. So if you do get a negative time, that means you've forgotten to think through the acceleration of gravity being retarding rather than accelerating. And we came up with 8.84 seconds. Okay? And then when we want to find the range, we can take that time times its horizontal velocity, which is 25 meters per second, and we came up with 221 meters, or about 2.2, really about 2.3 football fields. And then when we want to find the apex or height, we use our fourth kinematic equation, solve for d, realizing that at the top, and this is key, at the top your velocity is going to be instantaneously 0 before it starts down again. Dividing it by 2 times the acceleration, we come up with 95, or just under 100 meters. Okay? Now, I'm going to solve one other problem, and that is the problem that occurs with driving and accidents, and that is if a driver would be going down the road, fall asleep at the wheel, and go out and go over a cliff. Okay? That is another class of projectile problems. We're going to do that one. I'm going to erase the board, and we'll come right back with that. Welcome back. So I've cleared the board, still have my kinematic equations up there, which we'll use. And I've drawn a picture of a type of projectile, which is a vehicle driving along the road where the driver either gets distracted or maybe fell asleep and goes off the road at some initial velocity, and we're going to start with 20 meters per second going off the road. And it's going to then be accelerated by gravity in the vertical direction, and we're going to go down to this ground below this cliff 30 meters. So 30 meters is just about 100 feet, just for reference. And what we'd like to know is how far out from this cliff, once the car leaves the support of the ground, how far out, or the range of that motion, does the car go. Now, if you're a highway patrol person, this could be very important in an accident investigation. If you come to a cliff and a car you found down there, you can measure this distance and measure this distance, and then you can infer what that speed must have been for that vehicle to travel that far in that much vertical distance. Okay? So, this is actually an easier problem than the football punting problem in that we have no initial vertical velocity. Okay? So, what we're going to do is say we have no initial vertical velocity, we have an initial horizontal velocity. That horizontal velocity will never change because there's no force out here pulling it to make it go faster, or nothing back here that's making it slow down. So it's going to be moving along horizontally at whatever it left the cliff going, in this case 20 meters per second. We have to determine how long that vehicle is in the air before it hits the ground. The ground is 30 meters below. So we need to know the time that, that we have traveled to go from 30 meters all the way down to 0 down here, 30 meters of travel. Now this is very much like just dropping something right off the cliff, like a rock, and timing how long it goes, how long it takes to get down to where you hear it hit the ground, okay? So we need to find the time. Now let's see what we could use for that. We have a distance, we know the distance, okay, and we know the acceleration. We could perhaps use that. This one does not have time in it. We could perhaps use that in terms of its initial velocity would be 0, and we could find its final velocity, but that might be 2 steps. So let's just see what luck we have using this one, okay? So we're going to use D equals V0t plus 1/2 AT squared, okay? And this is in the vertical direction, going this way. Well, one thing we know is there is no initial vertical velocity because all its velocity is going this way, none going this way, okay? So this equals 0 plus 1/2. The acceleration is 9.8 meters per second squared. And t is what we're trying to find. So there's t squared. And the distance, we do know the distance, and that is 30 meters. So that might have been a good choice for us. 30 equals 0. Okay, let's go ahead and work that out a little bit. So there's my 30. This is 0. 1/2 times 9.8 is 4.9. 4.9 times t squared. Okay? So now let's solve for t squared. It's going to be equal to 30 divided by 4.9. Okay? So let's calculate that. 30 divided by 4.9 is 6.12. So t squared is equal to 6.12, and that would be seconds squared because that's time is squared. Let's solve for t. So t is going to be the square root of that. So let's take the square root of that. 2.47. 2.47 seconds. Okay? All right. That's the time until it hits the ground. Just like if you dropped a pebble from something that's 30 meters high and you timed it, it'd be 1001, 1002, bang, it hit. Okay? So now that we know that, we can come back and look at how far we're going to travel, and that is R, the range, and that's basically going to be just the velocity times the time. Okay? The rate distance equals rate times time, the old formula we've had for forever. Because there's no acceleration in the horizontal direction. So let's solve for R. Our velocity is given at 20. So we do that. We're going to multiply it by 2.47. we'll take 2.47 and multiply it by 20, and that's 49.4. Approximately 50 meters. Okay? So, as this is going off the cliff at 20 meters per second on a 30-meter cliff, it is going to end up hitting the ground approximately 50 meters away from where it left the top of the cliff. Okay? So again, as I said, if you're a highway patrol person investigating an accident, you could work this backwards, knowing what R is, knowing how far it must have fallen, and then back into what the velocity might have been, and that would tell you whether or not the driver was speeding and doing anything else that might have been illegal at that time. Right, so projectiles are very interesting types of problems. They are great examples of using the kinematic equations, and it's part of our everyday life. Much of what we do from childhood on to adulthood has to do with things that are moving and under the force of gravity, because that's the world in which we live. We have gravity all around us. So all our sports involve it. Our daily life involves it. When we drop something off the table or slide something off the table, we can predict what's going to happen using our kinematic equations properly. It's not a difficult problem as long as you follow the steps. Find the components, use the kinematic equations to find the variables that you're concerned about, and then properly execute the mathematics. So I hope you've enjoyed this, and we'll see you next time.